In this video, we will be going through solubility rules to determine if a precipitate will form from a chemical reaction, and we'll go through ionic equations that help determine whether a precipitate will form. So, with ionic solutions, when we look at an ionic solution, what is actually happening in the beaker? So, as we discussed the other day, when we have our ionic compound, in this particular case, we'll look at the example of sodium chloride, which starts out in that solid state. As it dissolves in water, those positively charged ions and those negatively charged ions will separate from each other and will actually be surrounded by water molecules as it goes in the solution. So we get our dissociation occurring. We have our ions in the aqueous state. But what happens when we mix two ionic solutions together? What is the result of that? So if we take a second container with a different ionic compound in solution, we add it into our first container. When those two ions mix together, what is going to happen? So we have our first ionic compound that we talked about in the previous slide. We have our second ionic compound now that we are adding into that solution. So when we add those two ionic compounds together in solution, each of them will dissociate into their respective ions. And from there, we need to figure out, is a reaction going to happen now? Are we going to form a new product? So to figure out if we will form a new product from mixing these two solutions together, we use what are called our solubility rules. So the solubility rules, and this is all about our ions. Will our ions come together to form a precipitate? So we have a whole list of rules that will determine whether a precipitate will form or not. So the first rule is that all nitrates are soluble. Anything that is a nitrate will be soluble in water. All ammonium, NH4, or alkali metal compounds are soluble. And by alkali metals, we mean the lithiums, sodium, potassium, and so forth. Those are the three main ones that we will deal with. All carbonates, phosphates, and hydroxides are insoluble, except with the cations listed above. And when we talk about something being insoluble, we mean it will remain as a solid in solution, or it will form a precipitate. So all our carbonates, phosphates, and hydroxides, they are insoluble, except if they're combined with the metals we listed above. So for example, sodium carbonate is soluble, whereas calcium carbonate is insoluble. All chlorides, bromides, and iodides are soluble except if they are paired with silver, lead, or mercury. So for example, if we have lead 2 bromide, that would be an insoluble compound, whereas sodium bromide would be soluble. All sulfates are soluble except with calcium, strontium, barium, radium, and lead. So for example, calcium sulfate is insoluble. Sodium sulfate is soluble. And the thing to note about our solubility rules is that these rules, with these rules, the higher up ones cancel out the ones below. So the higher up a rule is, the more precedent it takes. And you can refer to these rules on page 363 of your textbook as well. So looking at our solubility rules in a chart, and you guys should be drawing in these arrows to help organize and visualize this information. So once again, we start at the top. All of our nitrates are soluble. Ammonium and our alkali metals, they are soluble. Anything that is a chloride, so our Cl, our Br, our I, they are soluble except with silver, with lead, and with mercury. And our sulfates, they are soluble, generally soluble, except when we have them now paired with calcium, with strontium, barium, radium, and lead. And looking at what's considered insoluble, so our carbonates are all insoluble unless they are paired with our ammonium or alkali metals. And the same with our phosphates and hydroxides. So for example, calcium hydroxide is insoluble, whereas ammonium hydroxide will be soluble. So, making use of these solubility rules. We use what is called ionic equations to figure out if a precipitate will form or not. And so with these ionic equations, they are used to represent ionic compound reactions. So in the following example, we have a solution of copper 2 sulfate is mixed with a solution of barium chloride to yield a blue precipitate. So if we were to write out that reaction that would occur as we would have done previously, we have our copper 2 sulfate plus our barium chloride. When this reaction occurs, we get a double displacement reaction occurring. Where each compound, each ion now will trade partners, and we form new compounds. So we get copper 2 chloride being formed, and we get barium sulfate being formed as well. And note that you have to write in the subscripts of the states in each of the molecules that we deal with now. So based on our solubility rules, we know that all sulfates are soluble, except when bonded to calcium and other metals. Copper is not one of them, so copper 2 sulfate will be aqueous, meaning it will be soluble in water. Our chlorides are soluble, so with barium chloride now, that will be form an aqueous solution. When we have our double displacement reaction that occurs, we have barium sulfate being formed, and according to our solubility rules, all of our sulfates are soluble except with barium. So if we create the compound barium chloride, which we have done in this particular reaction, it will be insoluble, meaning it will form a solid precipitate. So we write a subscript S next to it. Our copper chloride will be aqueous because chloride, when combined with copper, will form a soluble solution. Again, according to our solubility rules. So again, our chlorides are only insoluble with mercury, lead, or silver. Anything else, anything else that chlorine is bonded to, will be solid, or will be aqueous, will be soluble. So in this case, our copper 2 chloride will be soluble. So in this situation here, we have to, when we represent our reactants and products as ions, which we're going to do in a second, we refer to this as writing a total ionic equation. This is where anything will be an ion in solution, we write it as an ion. So our reaction that we've been dealing with in the previous example, if we were to write that as ions, we would have copper 2 ions plus sulfate ions. We have barium chloride, which will break apart into its respective ions. So we have our barium ions in solution. And remember that we are dealing with barium chloride, which is BaCl2. So when barium chloride splits apart into its ions, it will generate 2 chlorine ions. Because I'm running out of room, I'm going to continue this just below. We know that we will form barium sulfate, which will be our precipitate. And for anything that is a precipitate, we do not write it as ions. We keep it as the complete ionic compound. Because it's not soluble in water, those 2 ions will stay bonded together. And we have our copper ions, and we still have our chlorine ions. And just note that the aqueous subscript is always written as its ions, and solid is always written as a compound or a precipitate. So when we write our ionic compounds as ions, this is what's referred to as our total ionic equation. So we've just taken our compounds and broken them up into ions. So when we look at this particular reaction, we have to ask ourselves, what is unchanged on both sides? So what remains the same? If we have a look, go back and have a look at our reaction, we'll see that we have copper ions on our reactant side. We have copper ions on our product side. So in this case, copper is unchanged. It's the exact same on both sides of the reaction. If we go back and look at our reaction again, we'll see that we have chlorine ions on our reactant side, chlorine ions on our product side as well. That is unchanged. So we can add in our chlorine ions to what is the same on both sides. Because our copper ions and chlorine ions are not directly involved in the precipitation reaction, we refer to them as spectator ions. And a spectator ion is anything that is unchanged on both sides of the reaction. So if it's in the same state on the reactant side and the product side, we refer to it as a spectator ion. Spectator ions we have no interest in. They're not participating in the reaction, so we don't really care about them. So what we can do is we can remove those spectator ions, and what we are left with is what's referred to as the net ionic equation. So if I take a second and just rewrite out that total ionic equation, so we have our copper ions plus our sulfate ions plus our barium ions plus our chlorine ions. This reacted to give us our barium sulfate, which was our precipitate, plus our copper ions and our chlorine ions as well. So now we've identified those spectator ions as being copper and chlorine because they are the same on both sides of the reaction. If we cancel them out because they are the same, cross them out, what we are left with is now our sulfate ions plus our barium ions reacting to give us our precipitate, the barium sulfate. With those ions that are left over now, this is what we refer to as our net ionic equation. So this is what is reacting within our solution, those barium ions, those sulfate ions, to produce barium sulfate. We ultimately don't care about those other ions in solution. So in the following, you're asked to consider the following reaction, where you're asked to use the solubility rules to identify the precipitate, if there is one, and to write the total ionic equation, and then eventually get to the net ionic equation in this reaction. So I will let you guys work through this example problem yourselves. In terms of practice, please work on page 410, questions 1 to 4, 6 to 10 as well.